So welcome everyone to our second talk today by Shreyas and Cheshta, and they will talk about their game QLogic, Gamifying Quantum Computing. Shreyas is a student from India, and he is a double major student in physics and computer science, and Cheshta is a master's student in physics. Now let's listen to them and listen their how they develop their game and listen their adventure.
So thank you so much for introducing us. Hello everyone, my name is Shreyas and I'm going to talk about QLogic. So QLogic is a game that me and my team have developed, and it's not a game that you play on a quantum computer, but rather it's a simulation kind of game which you can play on your phone. So if you have an Android device, you can get it on the Play Store. And QLogic is a puzzle game based on quantum logic gates. So that's where the name comes from. And till now, we've gotten a pretty good response from the community. So it has been covered in blog articles by Quantum Computing India and the Quantum Daily. And I would like to thank QWorld and QTurkey for organizing these talks and giving us this platform to speak on. So before we see the game itself, let's first look at how we got the idea for the game. So if you know computing, you know that there are these logic gates that we work with. So as far as classical bits are concerned, they would work with these kind of logic gates, and these will be present in all of the circuits around us. So this is the first logic gate we have, which is the NOT gate. And this is purely working with classical bits. It has a 0 as the input and 1 as the output. And on the right, you can see the truth table for this logic gate. It just converts a 0 to a 1 and a 1 to a 0. So that's what the NOT gate does. Next up, I have another example of a logic gate, which is a 2-qubit gate, the AND gate. Now, the AND gate just gives us an output of 1 when both of the inputs are 1. So the truth table would look something like this. And as a computer science student especially, I get to see these logic gates a lot. And here is a puzzle that you can try solving equipped with these two logic gates. So here is a puzzle. There's 2 bits which are starting off as the inputs in the 0 state. And you need to apply these NOT gates or AND gates, whatever you want, to the box that's given to you, and the output that you want is 1. So what I'm going to do is I'm going to give you a minute to solve this. And if you do solve it, put it in the chats. I think I should be able to see your comments. I can see one question in the chat which says, is that X? So we haven't gotten to talking about quantum gates yet, but the NOT gate is actually very similar to the X gate. So the AND gate is not actually the solution. I can see that as well in the comments, because the AND gate is going to give us 0, and 0 is going to give us a 0 and not a 1. So one of the solutions that I see is NOT and AND, and another solution that I can see is the NOR gate. So these are actually pretty good solutions that you've given. Let's look at the solution itself. So if you're thinking something of this sort, then you're completely on the correct track. So it's 2 NOT gates followed by an AND gate. What the NOT gates will do is they will convert the zeros to ones, and followed by the AND gate, which will take these 2 ones as input and convert it to a 1. And I can see one of the comments says a NAND gate. So that's exactly what we'll talk about in a minute. In this solution, you can see that you're using 3 gates. to do this, to solve this puzzle. So using 3 gates here is going to give you, let's say, something like 1 star out of 3. And the more effective solution using just one gate is something like this. We have the NAND gate, which was also mentioned, and another solution that was mentioned was also the NOR gate. So the way the NAND gate works is it's going to do an AND on these two bits and then do a NOT operation on that. So this solution, because it uses just one gate, it's going to fetch you something like 3 stars because it's a more effective solution. But what we have seen is just with classical gates, and they're similar to these classical gates. There are these quantum logic gates that we have in quantum computing. You probably know about these. So the first one we have is the X gate. The X gate will take a qubit in a 0 state and convert it to a 1 state. So here we've actually started working with qubits or quantum bits, which can be in a state 0, they can be in a state 1, they could be in superpositions of 0 and 1. So we've now moved on to talking about qubits, and this is the X gate converting a 0 to a 1 and a 1 to a 0, very similar to the NOT gate that we saw with classical bits. The second quantum logic gate is the H gate or the Hadamard gate. So the Hadamard gate will convert a 0 to an equal superposition of 0 and 1. And I know there should also be a factor of 1 by root 2 with the 0 plus 1 that I've written. But I've just decided to show an equal superposition of 0 and 1 and skip the normalization part. So the H gate will also convert a qubit in a 1 state to a 0 minus 1. So that's what the H gate does. These are a couple of quantum gates that we saw. And this is how you would normally enter into quantum computing. The first step would be to understand all the gates. The next step would be to design an experiment. You would either want to understand all of the gates or as many as you can, at least a few gates. And then you would want to design an experiment. So at this stage, you can design your own experiments, or you could take some of the existing quantum algorithms. So we have the Shor's algorithm, the Grover search algorithm, and all of these can actually be implemented using the quantum gates. Some of the quantum gates, we haven't seen all of them yet, but what you can do is you can try working those out with these quantum gates. So once you do have an experiment, or you could also do something like take a scientific paper and model an experiment that you can run as a circuit. So that is the second option that you have. And once you have an experiment in mind, once you have some kind of a quantum circuit in mind that you can make, what you would do is you would head over to a circuit composer. So there are a lot of circuit composers available, and what you can do is you can make a circuit using these quantum gates, and you can just try out the experiment. You can try it out on either a simulator, or nowadays there are actually options for you to run your circuit on a quantum backend. So this is what a circuit composer would look like. So I've just put some gates that I could think of and made a circuit. So this is what a circuit composer would look like. And the problem that I faced as a student who was just getting into quantum computing was the following. So I understood some of the gates, but then I had to design an experiment or come up with an experiment which I could run on a quantum computer, or I could make a quantum circuit for. So this is where I got stuck. I wanted to play around with circuit composers because I thought they were really cool, but I couldn't think of enough experiments to run on these. So I thought, just like we had those puzzles in classical logic gates, why not have puzzles with quantum logic gates? So here is one puzzle for you. I start off with a qubit in a 0 state, and you need to apply some gates in here and get it to a 0 - 1 state. So once again, I'm going to give you a minute and you can try working out the solution. While you do work out the solution, do put it in the comments. I can see your comments here. So we have a few people who have mentioned that the solution is X and Hadamard, and one of the comments says that I'm missing a square root 2. Yes, I am missing a factor of 1 by square root 2, which is something that we decided to actually avoid in the game, because the normalization part is something that actually complicates some of the stuff. So yes, we are missing a square root 2. One of the solutions I see is just an edge gate, and the edge gate will convert the qubit in 0 state to a 0 + 1. So there's still a phase difference that you need to fix. So let me move on to the solution. So here is the solution. If you're thinking of this, I did see a couple of comments who were thinking of this solution, and that's perfectly correct. The solution is to put an X gate followed by an H gate. The X gate is going to convert the qubit in a 0 state to a 1 state, followed by the H gate converting the qubit in the 1 state to a 0 - 1. And why is there a negative? If you're asking why there is a negative on the right hand side, that is just a state that has been given to you, and you need to find a way to get the qubits in that state. The minus actually refers to a phase difference. And this is just one solution that you can think of. There's also other solutions. If you know a bit about quantum gates, if you know about the phase flip gate or the Z gate, which converts a 1 to a -1, then what you could do is you could first apply the Hadamard gate and then follow it up with a phase flip gate, which is the Z gate, and that would also give you a 0 - 1. So with this puzzle in mind, I thought, why not make an entire puzzle game like this, where there are a lot of puzzles of this sort. So I thought we could make this a game, and I started building my team. So if you attended the previous talk, there was mention about how making a quantum game would involve a team of people, someone who would know game development, someone who would know quantum physics, and probably someone who would know graphics as well. So the first person would be me. So I'm Shreyas. I'm a computer science and physics major. So I'm doing a double major in India. So in QLogic, my role is focused towards the game development aspect. I've been developing games earlier as well, before QLogic. And with this idea, I approached Cheshta, who is a physics student at my university, and she is the chief quantum physics person in our team. So Cheshta is our physics person, and next we approached Namita, who is a user experience designer. As far as QLogic is concerned, Namita is the one who makes the entire look and feel of the game, how the screens look. So if you like the look and feel of the game, Namita is the person who is responsible for that. And soon after, we were also joined by Nikita. who is another computer science and physics major in India. So the four of us together came up with QLogic, which is the game that we have developed. It's available on the Play Store. So this is what a QLogic screen looks like. So this is the puzzle that we saw a few slides earlier itself. It's a zero state, which is the initial state. You need to apply some of the gates given at the bottom, and you need to get to the target state, which is the 0 minus 1. So this is what the game screen looks like, and the game is actually focused at simplifying a person's entry into quantum computing. So every time a new gate is introduced, there would be a pop-up like this before the level, which would tell you what that gate does. So this is the level which introduces the Z gate. So just before the level, there would be a pop-up which tells the user what that gate does. So we have tried to make the tutorials as simple as possible to simplify entry into quantum computing. And when you reach the control gates, there would be pop-ups for that as well, some information about that. So other than the pop-ups which come up before a level, in between a level, you can always hit the info button and you would get a pop-up like this, which tells you in a single line what each of the gate does. So this is another way with which we thought we could simplify the game and make sure that if you forget some gate, then you can quickly look at that gate with the info pop-up. And let's talk about the state of the game as it stands right now. So right now the game has 6 gates, which are the X, Z, and H, the bit flip, phase flip, and Hadamard gate, and the controlled version of these gates, which is the CX, CZ, and CH gates. And using these 6 gates, we've come up with 75 puzzles already. So if you head over to the game, there are 75 puzzles that you can try out. And we're constantly working on adding more gates, adding more puzzles to the game. And other than most of these gates, most of these levels are actually based on moves. So just like we saw earlier, you got a 1 star for doing a puzzle in 3 gates, whereas you got 3 stars for doing it in a single gate. Similarly, these puzzles would normally be based on moves, but we've also added some timed puzzles. So for the timed puzzles, you need to complete the level in some amount of time, let's say 60 seconds. You would have to complete it within 60 seconds. And the stars are also based on how much time you take for it. So if you complete a level with within 15 seconds, then you would get a higher score for the level than if you complete it within, let's say, 45 seconds. So there are timed puzzles as well. And then we have the playground. And if you've looked at Circuit Composer, you would know that QLogic as a game is very similar to a gamified version of a Circuit Composer. So it's just that in a Circuit Composer, you need to think about what the initial state is, what the final state you want, and once you do get the results, you need to draw your conclusions from there. As opposed to that, here we're just giving you some levels where you know the initial state, you know the final state, and you just work out what gates you need to apply. But we also have a playground where you can apply these gates, and you can just play around with it, and you can see that there's no move timer or there's no move counter or a timer where we keep track of what you're doing. This is just a safe space. And before we move on, I have a question here which says the game is only available on Android. So yes, right now the game is only available on Android, but we are working towards making it available on other platforms as well. So this is the playground where you can just try out the gates. And next, I'm going to hand over to Cheshta, who is going to speak about making a quantum game, making your own quantum game.
Yeah. Hello, everyone. Am I audible, Stress?
Yes, you are.
Yeah. Cool. So, hello, everyone. I am Cheshta. I am a final year physics undergraduate from BITS Goa, India. And I'm also a part of the QLogic team. So, yeah, it's great to see so many people interested in quantum computation. I'd like to know if you guys already have some background in quantum computation. A simple yes or no would do. So you can write it in the comment box. Anyway, even if you do not, Stress did a good job introducing you guys to quantum computing. He talked about the classical logic gates, the quantum logic gates, the quantum circuits, and how we came across the idea of QLogic, and also some basic features of our game. So yeah, I see a lot of yeses in there. So okay, it's great. Cool. So I am going to talk about how you can go about making your own quantum game. So the first thing that comes up to my mind when I think of making a quantum game is trying to take a classical game and an already existing classical game and adding a quantum move to it. Can you please go to the next slide? Yeah. So yeah. So the first method, as I said, is take an already existing game and see if you can try to add a quantum twist to it. So here are some of the games that I've mentioned here. We have quantum tic-tac-toe, quantum chess, and quantum battleship. Let me know if you guys have played any of the quantum version of these games. So these games are readily available online, and if you search quantum tic-tac-toe or any other game, you can find different versions devised by different people out there, and you can play them online. And even if you haven't, spoiler alert, the superposition and the property of entanglement is kind of the protagonist in most of these games. So let's say, for example, quantum tic-tac-toe. So what you do is that you're allowed to make a mark, let's say a cross or a zero, on two blocks simultaneously. So your mark exists in two places at the same time. And later, when a measurement occurs, it collapses to one of these blocks and the game moves into one of the two directions it is supposed to go to. So if you're putting one mark in two different positions, you can say that it is now a superposition of two games on one board. So that's about quantum tic-tac-toe. Then we have quantum chess. So recently, the first quantum chess tournament was organized, and the finals was played between Google and Amazon. I'd suggest you guys to go watch it and also try out this game. It's amazing. Again, it uses superposition and also entanglement to make the game more interesting. So what you can do is you can, whenever you select a piece, you can see the different moves you can make, and you can choose two places where you want your piece to be. And then again, later a measurement happens, and if the other party wants to move a piece to a place where you have a superposition of a qubit, a measurement occurs, and we see if the qubit is, if the piece is already present there, and according to that, the game moves ahead. Similarly, we have quantum battleship. One interesting thing about the quantum version of battleship, which is devised by James Wooton, is that it's run on an actual quantum computer. So you can check that out, and that's something really cool. And you can also try to make a game and try to run it on actual quantum computers. So that was the first way. The second way I can think of is to pick up a quantum property and devise a game around it, build up a game around it. So, like, I have a game here. We know qubits can be in different states. Let's say we have three different states: a 0 plus 1, a 0, and a 0 minus 1. Now, if you measure it in different bases, the probability of getting a 0 and a 1 for result, or an upspin or a downspin for result, would be different. And if you're given one of these cards randomly, then you can make a guessing game around it. So what you can do is measure the state you got once and try to guess which one you have. Now, let's take the example I just gave. If we have the state 0 plus 1, 0, and 0 minus 1, and if you measure it in the standard bases, then if you get a downspin, you can say for sure that you don't have the 0 state. And if you have, and if you get an upspin as a result, then you're not very sure which state that you have. So we can build up different strategies using measurement results, and we can make up a guessing game around this. So just like that, there are a lot of properties, a lot of phenomenon that you can use and try to build up a game around it. So the next thing we wanted to talk about was the points we considered while making this game. And some of the things that we came across and some of the things that we learned, we thought would be great for you too, and maybe they would help you make your own quantum game. So the first thing is keeping it simple. So one thing we tried to focus on was that we wanted the game to be beginner friendly. We wanted the people who do not have a background in quantum computation to be comfortable with this game too. So the first thing we did for this was that we took out all the amplitudes and all the normalization part out of all the qubits. So you can see we deal with the state 0, 0, and even after applying a Hadamard gate, as some of the people were indicating in the comments that we're missing a 1 by root 2. So that is just something that we decided to do, that we decided to abstract out all the mathematics, all the amplitudes, so that it looks like it looks more like a game, and the players are comfortable playing it. So that was the first thing that we did. Second was that we have this. We know a gate operation is, it looks so simple. Like in the previous slide, we saw there was just a control X gate. So that simply means that if the qubit 2 is in one state, then the qubit 1, NX gate would be applied on qubit 1. So it looks so simple on the face of it, but the mathematics behind is rather complicated. Like you can see that for making a control gate matrix, you need to use some projection matrices and tensor it with identity or the gate matrix and then sum them up. So we decided not to include all this mathematics part and just show the simple gate operations that were taking place on the screen. So what we want to imply from this is that your game could have complicated calculations and mathematics behind it, but you have to try to make it look simple to the players so that the players actually enjoy the game and also understand the quantum physics behind it, or the concepts of quantum computing behind it. The next thing we think you should focus on is working out all the possibilities of a quantum move or your quantum game. So let's talk about this level here. So we need to take this zero state to the 0 - 1 state. And as we discussed earlier, you can do it in two ways. The first way is to apply an X gate and then an H gate. So that's the first way we can solve it. And the second way, it's shown in the slides, in the next slides. The first way is to put an X gate and an H gate. The second way is to put an H gate first and then a phase flip gate. So both of these ways are valid, and in fact, you can come up with many more ways of getting a zero state to the 0 - 1 state. You can keep on adding different gates infinitely and still get to the 0 - 1 state. So that was one thing we had to consider, that we cannot judge how the player is reaching to the final state. So we had to devise something to judge how a player is clearing a level. So we decided to keep the moves counter. So now what we do is we rank the player on the basis of the number of gates they've used instead of the way through which they're reaching the 0 - 1 state or the final state. So that is one thing we want you to focus on, that whatever quantum property that you're using in your game and whatever so whatever quantum property you're using in your game, you have to work out all the possibilities. You have to step into the shoes of the player and think about all the different possibilities and try to incorporate them in your game. And so that was all about what we learned. And you can develop any quantum game, take any quantum phenomenon, and try to build up a game based on that. You have to focus on just you should focus on trying to give a message to the players, or maybe if you focus on teaching something quantum, that would be great. You can work on any different field you want to. Maybe you can use something from quantum optics or quantum cryptography and build up a game around it. And we're really excited to see what all you guys come up with. It's such an amazing event, the Quantum Games Hackathon. So yeah, I think we're done with the presentation. Let's switch to the demo part now.
Yeah, so I hope you can see the screen. I'm running an emulator which runs the Android game here. So this is what the game looks like when you open it up, and when you hit play, then it's going to give you all of these levels. So as we mentioned, it has 75 levels right now. And when you just start off, when you go into level 1, it would give you a pop-up which just tells you about the X gate or the bit flip gate, because that was the one we thought would be the simplest. So it's a very simple instruction on how the X gate works, and I can hit OK, and I just take this gate and place it right here. That completes the level for me. So I get 3 stars because I solved it in a single gate itself. So this is how this is what it looks like. And then when I head to level 3, I would get some instruction on the Z gate as well. So this is how we've given some tips for all of the gates. And now let's take a look at the level that we've been looking at for a while now. So we have this level right here, converting a 0 to a 0 - 1. So there are 2 solutions. One is to either apply the X gate followed by the H gate, and the other is to So let's just look at this first. And this, you can see that it gives me 3 stars. So not just are both of these solutions correct, they're also both worth 3 stars because both of them just used 2 quantum gates. So this is what this level looks like, and you can solve it using multiple methods. And then let's take a look at another level, which is this one right here. Now my aim is to convert a 0 1 to a minus 0 1 to a 1 1. And as far as I'm concerned, the most intuitive way to do this is to apply an X gate to the first qubit, followed by a Z gate to the first qubit. That should do it. But then I realized that here I don't have the X gate at all. So what we have done is, in a lot of levels, we have removed the most intuitive gate that you would think about. So now what you have to do is you have to think of how you can use the H and the Z gates to complete this level. And if you want, you can start putting any solutions you have in mind in the chat box. So let me actually not just wait for your solutions, but I'm going to start solving it. So what I do is, first thing, I don't touch the second qubit at all. It's in state 1, so I keep it in state 1. So what I start off with an H gate on qubit 1. And I'm using an H gate because the Z gate isn't going to make sense at all, because it's already it's in state 0. My qubit 1 is in state 0. So one notation that we have followed is the qubit on top is always the leftmost qubit that's represented here. So I apply the H gate, and then I apply the Z gate, which and follow it up with another H gate. And what this does is it gives me a minus 1 1. So having gotten here, I can just apply the Z gate, and doesn't even matter which qubit I apply it to. What I'm going to do is I just apply it to the first qubit, and that completes my level. So this is something else that we have done. We have restricted some of the gates in a few of the levels. So that was this one. And then let's look at another level, which is this one right here. So here I have 0 1 plus 1 1, and I need to take it to 0 1 plus 1 0 minus 1 1. So this is actually, because this is level 23, it has stepped up the difficulty a bit. So this time what I can think of is, first off, I'm going to get a 1 0 here. So I already have a 0 1 on both my current and my target state. So let me try and get a 1 0 on the left. So what I can do is I could just apply a control X gate. So that does give me 0 1 plus 1 0. So I have this part right here, and now I need the 1 1. So what I do is I apply a control H gate to the second qubit with the control on the first. So it's going to use this one as the control, and then do the H operation, which gives me a 1 1 as well. And now all I need is the phase difference. So I need a minus 1 1 here. And I can't use a Z gate, because if I use the Z gate on the first qubit, then it's going to alter the state for this 1 0 as well. If I use it on the second qubit, then it's going to alter the state for 0 1 as well. So what I do is I use a control Z gate. A control Z gate will just do the operation when both of them are 1. So this completes my level, and I did this with the most intuitive approach in mind. But as you can see, I've just got 2 stars here. So the 1 star solution is actually very simple. All I have to do is I take the control H gate. I use the first qubit as the control. So it uses this one here as the control. And I apply the H on the second qubit, and that actually just solves my level. So this is solving it in the most efficient gates with the most efficient gates. And next, let's look at a more complicated level. So let's look at level 65. So because this is level 65, this has gotten a step even more difficult. So we have 3 qubits this time, and we have 3 terms on the left and 4 on the right. So this is one of the tougher puzzles that we have, and this will take some time for you to work out. And what you can do is you can start off with some control gates and try to get 4 terms first, and then try to match the current and the target states. So you could try doing that, but the actual solution is actually very simple. Even though this is one of the tougher levels, it's just tougher to work out. But as far as solving is concerned, what you can do is you can just apply a control edge gate like this, and your level is solved. So that was about levels with increasing difficulty. Now let's look at a timed level. So we mentioned that there are also some timed levels in our game. So we have level 32, and now you can see instead of keeping count of my moves, it's keeping count of my time. And what I have to do is I have to do a 0 1 plus 1 1 to a 0 1 minus 1 0. So what I'm going to do is I would apply an X gate on the second qubit. That gives me 0 0 plus 1 0. Now I just need to convert the 1 0 to a minus 1 0. So I apply a Z gate on the first. So this solves it, but now as you can see, it just gave me 1 star, even though I solved it in just 2 gates. And that was because I used a lot of time. So I've used, I'm just left with 26 seconds out of 60. So if I instead restart the level, and if I do it within less time, then I can get a better score on this level. So now, as you can see, I've got a 3-star solution. That's because I did it in just 6 seconds. So this is about timed levels. And now let's look at something other than the levels, which is the playground. So when I open the playground, it gives me an option of how many qubits I want to work with. And this is this isn't a puzzle. It's just me trying out gates on different qubits. And when I do have 1 qubit selected, it's only going to give me the 1 qubit gates as options. If I switch to 2 or 3 qubits, it'll give me the multi-qubit gates as options as well. So let me select 3 qubits. And now what I can do is I can apply these gates as I want. I can just try out the gates and see what they do. And one very interesting thing about the playground is if I applied this gate, but then I realize that this is not something that I want, I can hit the undo button here. So I hit the undo button, it removes the last gate that I used and changes my current state. So this is how the playground looks. And like I mentioned in the slides as well, you can hit the info button and just get the info on these gates. So this is the playground. And as far as the undo button is concerned, the undo button is not available on the levels, on the puzzles. If you apply a gate and you realize that that wasn't something that you intended to do, then you would have to start the level over again. And the reason we have done that is because the undo thing is soon going to be added as a power-up in the game. So if you notice, even in levels, I would sometimes get this Q coin symbol right here, which I have in the bottom right. So that's the Q coins, which is the in-game currency that we have. And what's soon going to happen is you'll be able to buy some power-ups using these Q coins. So the kind of power-ups that'll be there is one is undo, of course. The other might be something like added time in the timed levels. Another thing could be a hint for a level. So these are the kind of things that will be added. And last, let's look at the time attack mode. So the time attack is one of the most fun modes in the game. And the time attack has two modes, which is the 2 and 3 qubit modes. So what I can do, what I need to do in the time attack is I need to get as many unique states as possible. So right now it's at 0, 0. If I apply an X, let's say, I get a new unique state. I get a +1 here in my score. If I apply the X gate here, that's 1, 1, which is another unique state. I get another +1. And if I apply an X here again, I go to 0, 1, which is another unique state. And now let's see, if I go to a state that I already had before, it won't give me any new score. So this is what it looks like. And if I apply an edge gate, that gives me an added score of 2. If I apply an edge gate here as well, it gives me a score increment of 4. So my aim is to get a maximum score by achieving as many unique states as possible. And let me tell you a bit about the scoring system of time attack. So the way the scoring system works is if the state that you obtain has 4 terms separated by plus or minus, then you get a +4 for achieving that state. And if it has, let's say, 2 terms, then you would get an increment of 2 for that state. So this is how the time attack scoring works. And with this time attack scoring in mind, I'm going to leave you off with a question, and I'm not going to be answering this question. This is something that I would want to leave you with. You can work this out sometime. So what do you think is the maximum score that can be achieved in 2-qubit time attack? So that would depend on the number of states and how many terms you can have in the states. So that is something you can work out. And I'll let you in on a very interesting thing. Once you do work out what is the maximum score possible, what you can do is you can try achieving that score in the time that's given to you. And once you do that, there's going to be a global leaderboard where we'll display the highest scores of time attack. You'll be able to add a display name for yourself, and you'll be able to see the highest scorers of time attack. So do try to get the highest score after working out what the highest score is. Do try to get it. We'll see you on the leaderboards, which we are going to be adding very soon. So do try out the game, and thank you. If you have any questions, you can ask them now.
So thank you, Shreyas and Cheshta, for this great talk, and thank you for accepting our invitation. We have small time for some questions. You can ask it in chat. We had some questions asked in the form. One of them was from Ioannis Theodonis from Greece. Is there a global rating system? And you just mentioned about it, so it will be soon added. And there was another question from Vardhan Mongia from India. Where do quantum games fit as a teaching aid? So what do you think about it?
So yeah, I think quantum games can actually be very helpful in teaching. And even more importantly, circuit composers are already being used for teaching. And quantum games would also fit into not just teaching, but also learning. So when we do attend a class, you would learn about these gates, but to actually understand these gates, it would be very helpful. And it's also helpful to teach using a game, because that makes it even more interesting for people to learn. So I think it would be a really great teaching tool as well. And it need not be just puzzle games. Puzzle games are something that we're just starting out with. But as Cheshta mentioned, there's also quantum chess and all, which tell us about superposition. So that is something very exciting. You get to see what superposition is. Superposition is a chess piece being in 2 places at the same time. So that does help get a very good intuitive understanding. So yeah.
So thank you. I really like the game, and I think it will be really useful when you are learning about the games and their actions, and you do it through a game. So I think it's really nice. So thank you again for coming and joining us. In 10 minutes, we have the next talk by Laurent Nita, and he will talk about Quantum Odyssey. You know the link. So let's see everyone in 10 minutes. And thanks again for coming. And,
All right. Thank you so much for
Thank
giving
you.
us this platform and opportunity to talk.
Okay.
Thank you, everyone. Thank you, Muslim.
So thank you everyone for attending. Thank you so much for giving us this opportunity.
So thanks everyone, and see you.